Today is going to be the first of several lectures on enzymes. And so today we're going to focus on what is an enzyme, what does it do? And next lesson we'll focus more on how does it do it? And then we'll talk about, well, what keeps it from doing it? So inhibition, as well as how fast can it do it? So kinetics. But first, we're going to talk about just the basics. Enzymes, reaction coordinate diagrams, free energy, all of these things. Let's go.
We can think about a crayon and think about it snapping. It's not just going to snap on its own, right? You have to put some work in to actually get it to snap. So it might be that the crayon is a lot happier when it's in the snap form, and you might be a little happier if you had something against Crayola. But bottom line, it doesn't just happen on its own. No matter how favorable a reaction might be, it's not just going to happen. That bag of sugar is not just going to combust because it's around oxygen. Instead, there's going to be like a high activation barrier to reactions happening. And so when we talk about like thermodynamic favorability, that's really only a part of the picture. In order to get reactions to happen and to at like a reasonable rate, and to get specific reactions to happen, we need enzymes. We need reaction helpers, speed uppers, reaction mediators. We need proteins typically that are going to pull things together in the right place, in the right orientation, help things get into that really, really awkward state right before it snaps, stabilize that what we call transition state. Enzymes are going to do all this great stuff. They're going to make it easier for the reactions to happen, allow reactions to happen in the first place. We're going to talk all about them. So we'll have lots of lessons to enzymes, but hopefully you'll see that there's a lot of details that I don't need you to worry about, and really I want you to focus on the fundamentals, being able to follow reaction mechanisms, being able to interpret reaction coordinate diagrams, and being able to kind of see the trends that are in play. Because kind of like organic chemistry, you had all the different mechanisms, but it was really like the same thing over and over again. If you think about nucleophile attacks electrophile, same deal here. We're just making it easier for that to happen.
Enzymes can use a variety of different strategies to make reactions happen, and different enzymes can catalyze the same reaction in different ways or catalyze different reactions in the same way. And we'll get much more into these catalytic strategies in a further lesson. But for now, just kind of this is just what to keep your eye out for. All the enzymes are going to do proximity catalysis. This is also known as entropy reduction. Basically, they just bring things together. They make it easier for them to react. They hold them in the right position to react. We'll see acid-base catalysis. With acid-base catalysis, here what you're doing is you're actually going to be giving or taking protons, and this is going to help make molecules more reactive so that they are going to react. We'll see this a lot when we have like nucleophilic reactions. We'll see metal catalysis. Metals are great. They can serve as these kind of like coordination hubs, hold on to multiple things. They've also got that positive charge that's great for holding a negative charge and helping stabilize negatively charged transition states. We'll also see examples of covalent catalysis where the enzyme is actually making a temporary link with the substrate. So instead of just giving or taking protons from it or something, it's actually getting stuck on it. So it's like you go when you try to cut something and your scissors get stuck on your paper, and then you finally get the paper off. So that would be like a covalent catalysis. And we will look at examples of all of these different types of catalysis being used in kind of the same sorts of reaction, a protease, where you're kind of cutting a protein. And so not all of that will be in today's lesson, but these are the kind of things to keep in your mind when you're thinking about enzymes. And hopefully you'll see that although there's a lot of different enzymes, and the mechanisms can look pretty complicated, it's these same main things that come up over and over again. We'll also look at a little more complicated things when we're dealing with redox and stuff. But bottom line, these are the key ones. Keep your eye on them. We'll return to them in next lesson. So let's start by talking a little bit more about what enzymes actually are. So enzymes are typically proteins. They can sometimes be protein and RNA, sometimes RNA itself. We call those like ribozymes, but we're just going to be focusing for the most part on simple protein enzymes. And what these are going to do is they're going to make it easier to reach equilibrium. They're going to speed up reaction rates, but they're not going to change whether or not a reaction is thermodynamically favorable. And so, I've been going on and on and on about like kind of like thermodynamic favorability, but trying to make you see like it's not actually, it doesn't mean likely. Whether or not something happens is also going to depend, and how fast it happens is going to depend on how hard it actually is to get to that thermodynamically favorable state. So I like to think of things as kind of there being a pot of gold at the end of a rainbow. If you're on one side of the rainbow, you might really, really want to go get to that pot of gold, but you have to climb over a big rainbow in order to get there. And this is like a reaction with this is like any sort of reaction, even a reaction with a really big negative delta G. So even a reaction where the products are going to be much more favorable than the reactants, it's not like they're just going to poof, go and form the products right away. Instead, there's going to be some sort of barrier in the way, some sort of activation barrier. And this barrier can be really, really tall. And so your sugar and that bag of sugar you have isn't just going to like explode, and because it would be favorable to be in like all the broken up state. That's like, we break down sugar in our bodies to get energy, but if we have sugar and oxygen, it's not just gonna like poof, like go and produce all this energy. Instead, there's going to be a bunch of activation energy that's actually going to be required in order for things to happen. And what's going to happen is that enzymes are going to make it so that, yes, there will still be an activation barrier, but it won't be as dramatic. And the enzyme is basically going to lower the activation barrier, and we'll talk about ways in which this can happen. But what's really, really important is that the enzyme isn't going to change that overall favorability. And it's not going to be able to make something thermodynamically favorable that wasn't, or won't it be able to make something unfavorable that was already favorable. But remember that when we're talking about the delta G, when we're talking about this change in free energy, this is going to be talking about like at equilibrium. If you were to just like put those reactants together and go for a walk and you come back, are they going to have reacted or not? Well, the activation barrier is going to depend on that. But say you go for a really, really, really long walk, like years and years and years and years and years, and come back. Well, now what are you going to find? Are you going to find it mostly products or mostly reactants? And so that's what delta G is telling you about. It's telling you about if you were to let things reach equilibrium, what would you find more of? But in order to get over that, remember, you have to get past that activation barrier. And the top of this activation barrier is a point we call the transition state. And we often show it as this kind of like double dagger. And so this double dagger is representing the transition state, which is kind of the tipping point. So it's not an actual like reaction intermediate. It's not like a finite thing that you can detect. It's that fleeting instantaneous moment when you're like on the tippy top of that rainbow. So you need some energy in order to get to that top of the rainbow. But then what's going to happen is once you're at the top and you're at that tipping point, you're at the transition state, well, now you can go either way. If you go to the more favorable side, well, then you're going to be in a state that it requires even more energy in order to get to that top of the activation barrier. So you're more likely to stay in that favorable state. And if you were to tip the other way, well, then you would be able to go back up to the top of the rainbow more quickly. So the change in the difference in the energy between the products and between the reactants is going to determine your delta G. It's going to determine, okay, well, if you let them reach equilibrium, what would the proportions be? So remember that delta G is a state function. It depends only on the initial and final states. So it depends only on like your reactants and your products and the difference in energy between them. But the path to get between them can be very, very different, and the enzyme can alter this path. We're going to talk a lot about different ways that the enzyme can do this, such as by having like binding interactions that are going to offset the cost to get to that activation energy, as well as they'll also provide our specificity. And so we'll take a look at this sort of thing in a minute. But first, we've been talking about like reactants and products. But when we're discussing enzymes, we're now going to switch to talking about substrates and products. So we call our reactants substrates in the case of enzymes. So remember, we could use that word ligand to talk about a binding partner, and we said that was kind of like a generic term. Well, substrates are going to be the binding partners of enzymes that the enzymes are going to act upon and change in some way. So remember, S substrates are the S starting materials for enzymes. So it's not just a ligand. So enzymes can bind other things too, when we can talk about like enzyme cofactors. And we will talk about enzyme cofactors. These could be things like metals, or they can be things like vitamins. And these can be important because they're going to provide additional functional group opportunities that a protein alone wouldn't have. We can talk about an apoenzyme, which is an enzyme by itself. And then it has like a cofactor, and when they're bound together, you get a holoenzyme. And so there are different types of cofactors, including those metals, including organic compounds, things like vitamins, and we'll see lots of examples of those come into play. But in terms of the substrate, that's the thing that the enzyme is actually going to modify. So this would be the crayon that we are going to snap. And then the place where that binds is going to be the active site. So the active site is the part of an enzyme where the action happens, where the substrate binds and gets changed. Now, if you look at an enzyme, it might be really, really big, and there might be a really, really small active site where that substrate is actually binding, and there might only be a couple of amino acid residues that are going to be really important. We often call these like catalytic residues. You might have some catalytic residues that are actually directly helping make the reaction happen, and then you might also have some residues that are important for binding the substrate directly. But so why do you need that whole enzyme overall? Why do you need the big old protein? There are a few reasons. One is that it might have like binding sites for other things that's going to allow for regulation. But one of the most important things is that basically you're going to have you're going to actually make a lot of interactions with the substrate, even if there's only a couple that are making really key ones. Basically the whole enzyme has to adapt for that. And so you often get these like changes in the shape of the enzyme. You get this kind of like induced fit we'll talk about, where the enzyme is kind of molding itself around the substrate. And all of that is going to require changes that are far away in the enzyme, just like we saw with hemoglobin, how something happening in one part can like lead to a ripple effect, like an allosteric effect. We can get things like that in enzymes too. And we're going to have, like I said, there's often like some very critical interactions, but then there's also like networks of interactions that are going to be binding to this substrate. And all of these individual weak interactions are going to provide the energy for the catalysis, as well as provide specificity. So we're going to have lots and lots of these weak interactions. And sometimes, as we'll see, we'll also have covalent interactions. But if you didn't have that big old enzyme, you wouldn't be able to get all those interactions. You wouldn't be able to get all that specificity and that sort of thing. So that's why enzymes are a lot bigger than you would think that they need to be. And remember that enzymes are going to catalyze the reaction in both directions. So no matter how high the transition state, the ball can still drop either way just as easily. You can slide down either way of the rainbow just as easily. But if you go when you reach that pot of gold, then you're less likely. It's harder for you to climb all the way up the rainbow. There's a higher cost to get back up. Your activation energy would be even bigger to go from the products to the tipping point than it would from the reactants or from the substrate to the tipping point. And note that we kind of like simplify things when we go from like E plus S. So basically our enzyme and our substrate not interacting to ES. When they're interacting, to the E plus P when they're like the products are released. But this is actually a little more complicated, because what you have is you have the binding, then you form your complex with the substrate, and then you have to actually change that complex into product. But right now they're still going to be stuck to one another. So you'd actually have EP, and then the EP has to get released. So even here I've simplified it. But you're actually going to get these intermediates where the enzyme is going to be bound to the substrate, or when the enzyme is going to be bound to the products, and then those have to be released. But overall, we get this equilibrium happening that we can kind of just represent with this simplified notation. But as we see with our reaction coordinate diagrams, you will see those different states. So let's get into talking about those reaction coordinate diagrams. So this is going to, on the y-axis, we'll have our free energy, so our G. And on the x-axis, this is just like an arbitrary like reaction coordinate. So it's saying as the reaction is going along, this is the change in the energy. It's not telling you about any specific time or anything like this. This tells you nothing about the rate. It's just telling you about like place in the reaction. So you can make this super duper duper wide. You can make this super duper skinny. Basically, you just make it enough so that you have enough room to plot all of the different points you need to plot. Now, we're delta G, that's the difference between our substrate and our product. And remember that a negative delta G is thermodynamically favorable. That's saying if we let them reach equilibrium, you'd find more products. If we let the leprechauns hang out by the rainbow, you're more likely to find them by the pot of gold if you let them reach equilibrium. And alternatively, a positive delta G is thermodynamically unfavorable. This is saying that, well, if you have a positive delta G, that would mean that your products had a higher energy than your substrates, and this would be unfavorable because you can think about it, okay, well, now it's easier to get to the other side of the rainbow back where there wasn't gold before. So, and then the more negative delta G is, the more favorable things are in the downward direction. So the farther down this P state is going to be, the more favorable it is. And the more favorable it is, the harder it is to go in reverse. So you can see in this chart from the book, basically, the change, the activation energy. So the transition state, remember, is like this double dagger. And so the delta G double dagger from your substrate to your product. So basically this part, this activation barrier is going to be smaller than the activation barrier to go from P to the tipping point, to that transition state. Okay. And then basically the delta G naught, that's telling you like between your S and between your P. Because remember that you're not changing this delta G. This is the delta G. And then this is just like the delta G double dagger. So basically you're adding you have an additional step in between these, but delta G is the state function between just the S and just the P. Because remember, when you have this going up, you also have this coming down. So these cancel each other out. When you're going like up, you have to get to the top of the hill, but then you get that energy back when you go to the bottom of the hill. So this is going to cancel each other out and not contribute to your overall delta G, but it will contribute to the speed at which the reaction happens. But delta G itself is that state function. And to remember that delta G isn't always going to be negative. The enzyme can't change that, but it can offer alternative routes to get to the products. And these routes can have lower activation barriers that make it more likely to happen. So things can get more complicated looking when you're talking about enzymes. You have these like multi-peaked reactant coordinate diagrams where the troughs are basically intermediates, and then the peaks are going to be transition states. And yes, I said states, there are multiple transition states often. But typically there's going to be one that's going to be bigger than the others, and this is going to be your rate limiting step. No matter how complicated your diagram looks, no matter how many peaks, the rate limiting step, the transition state we care most about, is going to be that one that has the highest delta G double dagger. So the one in which there's that biggest barrier to reach. This is going to be your rate limiting step, because no matter how fast the stuff is going on this side of it, and no matter how fast the stuff is going on this side of it, it's all like everything, there's this hold up here. And so you can have this big pile up of stuff before here, but that wouldn't really pile up because of equilibrium and all that. So bottom line, this is going to be your rate limiting step. Once you get over that, then things will go more easily. And sometimes it might be the first step, sometimes it might be one of the last steps, but this is what it would be. And that would be your rate limiting step. So how are enzymes actually going to be lowering the activation barrier? They provide binding energy that offsets what would have been the uncatalyzed activation barrier by forming favorable interactions and or covalent bonds with the substrate. When we talk about like bonding energy, when we talk about interactions, so interactions that are either covalent or non-covalent, all of our good old IMFs, what we're talking about is change in enthalpy. And we have to say, okay, are the new bonds and interactions more favorable than the old ones? So remember, these can be a lot of weak interactions. They can be things like even our transient interactions, or they can be stronger interactions. So remember, when we're talking about our intermolecular forces, in order of decreasing strength, we have our ionic bonds, our salt bridges, hydrogen bonds, other permanent dipole-dipole, other transient dipole-based attractions. All of these are contributing, and all of these are relatively weak. So all of these are going to, though, contribute to enthalpy. And remember, if we think back to our enzyme substrate, the protein structure, we have that big old structure, that big old enzyme kind of like hugging the substrate. All of those interactions, those nice warm, cuddly interactions, making the substrate more comfortable. Those are going to be more, if they're more favorable than the interactions that you had to break, well, now you're going to get that binding energy, and that binding energy is then going to be able to be used to offset the cost. Basically here, this like delta GM, it's talking about like magnet because it's this weird thing from your book, but you often see this like written as like delta GB. This will be your binding energy. And it's basically the difference between the uncatalyzed and the catalyzed versions. But now let's think about where we actually want the enzyme to be hugging our substrate, like in what form? Okay, now go ahead and take your crayon and hold it really, really tight. Is it breaking? How about now? How about now? No, if we bind it really, if we're holding it on really, really tight when we're bound to the substrate, that's not going to be helpful. In fact, it's going to make it harder to change it. We're going to be stabilizing the substrate form. But now go ahead and start trying to bend your crayon. Do it slowly so you don't snap it too fast, and try to get to that really awkward point at which feels like it's about to break. Go further, snap. That point at which it snapped, that is your transition state. Okay, and that is the point that you want to actually be stabilizing. That's going to be the part at which you have the highest activation barrier. That's going to be the part at which is hardest to reach. And so you want to lower the cost to reaching that. And the best way to lower the cost to reaching that is to make it so that your most favorable interactions are at that point when the crayon is about to snap. Now hold on to the products really tight, those crayon pieces. Okay, pull them on. Keep holding on. Okay, now go and break another crayon. No, I didn't say release your crayons. See, if you're held onto the products, that's going to make it work. You can't reuse yourself. So that wouldn't be helpful either. And so we want to stabilize that transition state. This is what the enzyme wants to do. This is what the enzyme is going to do. But so imagine that transition state. You had to put a little work in to get there, right? You had to be providing all that like binding energy and stuff. You had to be kind of like stretching yourself, your hands. You couldn't just start with your hands in the state at which things broke, or else the crayon wouldn't fit. And so in order to have that crayon fit in that transition state, we basically have to have this thing called induced fit, where the enzyme is kind of going to change shape a bit. So remember, when we have a protein change shape, we call it a conformational change. So the enzyme is going to kind of undergo a small conformational change, or it could be a bigger one, but it's kind of going to cradle that substrate and kind of like move it to that awkward state. But at that awkward state, that is when you have the most of those favorable interactions. And so you might have heard of like a lock and key mechanism where, the substrate is it like a key that fits in the lock, which helps explain why enzymes are really specific. But really, it's more of this like induced fit mechanism. And instead of the key like being in its normal key form, it's in like this bent form, or your whatever. Hopefully you know what I'm talking about. Basically, we want to stabilize that transition state. So in your book, they're showing an example of this where basically they're imagining this stickies where there's magnets that are acting to provide the binding energy. And they're showing like, yeah, if you stabilize your substrate, well, now what's going to happen is that you're going to raise your overall activation energy because you're lowering where you're starting from. And so remember that the points on here, these are basically representing these intermediate. So this is saying this is the complex of the enzyme and the substrate. So here you have enzyme plus substrate. Here you have enzyme substrate. here you have your enzyme product. They're not showing the release of the products. So sometimes you'll see like a second state. People draw things different ways, but basic bottom line is you have a bigger activation barrier if you were to stabilize the substrate form. But if you stabilize the transition state, well, now you're basically able to lower that cost. Okay, so let's get a little more into what a reaction intermediate is versus a reaction transition state. So intermediates are actual isolatable, or at least theoretically isolatable if you have the equipment, and some of these are longer lived than others, but they're stable enough to detect. But transition states, on the other hand, are fleeting and not isolatable, so they're super duper unstable. They have a lifetime that's shorter than a bond vibration. But we know they exist. I mean, they must exist in order to get from that unsnapped form to that snapped form. You have to go through that point at which things snap. You have to go through the top of the rainbow. The top of the rainbow is just a lot sharper than it actually looks in the diagrams. And so kind of like Santa, we know he exists because we see this presence in the morning, but we're unable to capture him in action. Okay. So these involve like partial bonds forming and breaking and partial charges. And so they're often really, really awkward. And the enzyme is going to be able to kind of do things like provide the opposite charges and things like this to help stabilize them. And again, the transition states are typically indicated by these double dagger symbol, and the transition state will often be shown in brackets. Quick word of caution though, sometimes you'll see that intermediates are shown in brackets, but typically you'll only see that double dagger in the case of a transition state, which often isn't actually shown. So to show you an example and to try to help directly see what's a transition state and what's an intermediate, we need to review our arrow pushing. So remember the rules for arrow pushing from organic chemistry. Your arrows are going to start at a lone pair of electrons or a pi bond, so like a double bond or triple bond. And they're going to always go from nucleophile to electrophile. So remember that our nucleophile, they are the things with typically a lone pair of electrons that is going to seek out some positivity. They want someone to share their electrons with. So they're going to look for protons, and protons can be found in the nucleus, hence the word nucleophiles. So they love the nucleus because that's where the protons are. They're going to seek out something that wants to share some positivity. So electrophiles, basically, they want more electrons. And so these are what the nucleophile is going to attack. By attacking the electrophile, well, now you can do things like form new bonds, form double bonds, or deprotonate, all this good stuff. It starts with the nucleophile attacking the electrophile, and this is what you're going to represent in your arrow pushing diagrams. In terms of the nucleophiles that we'll see in biochemistry, these are often going to be things like hydroxyl groups. Deprotonated is especially strong. We'll see amine groups. We'll see like the histidines and imidazole ring. We'll see double and triple bonds. In terms of our electrophiles, we'll be dealing with things like the C and carbonyls. This is going to be a really big one. So the oxygen is going to be pulling away from that carbon, making the carbon partly positive. Another common one is going to be the P in phosphates. And so similarly to how the C was partly positive because the oxygen is pulling away electrons from it, the phosphates in these phosphate groups are going to be partly positive because the oxygens are pulling electrons away from it. And we'll also see things like an ammonium cation serve as our electrophiles. In terms of the reactions that we're actually going to see, so remember, you start from your nucleophile, you go to the electrophile, and then what happens is going to depend on the reaction mechanism. So you might kick off the leaving group, get a new, like a substitution reaction. You might get an elimination reaction. You might just like steal a proton. So all of these can happen, and this is just happening from going from a nucleophile to an electrophile. So for example, if we had a nucleophilic addition and elimination to a carbonyl group, which we're going to see over and over and over again, what we would see is that basically we have a nucleophile. Remember, often a nucleophile is going to be a lone pair and an oxygen or a nitrogen, and our electrophile is often going to be a carbonyl carbon. We draw our arrow from our nucleophile to the electrophile. So in this case, our nucleophile is going to be the oxygen on this water, and our electrophile is going to be this carbonyl carbon. When we have them attack, basically what's going to happen is ultimately we're going to form a tetrahedral intermediate. So an intermediate, we have actual bonds here. But in order to get that to that point, we first had to have a partial bond being formed and this partial bond being broken. So this is our transition states. This is what we put in brackets with the double dagger. This is what the enzyme is going to be the most stabilizing to and provide the most help for. Additionally, we would also have another transition state on this side of the intermediate as we go from having these bonds formed to then breaking off this other bond. In this example, they're only showing the transition state, this transition state, because this is going to be the slower one, the rate determining step. But you are also going to have a transition state on the other side, and so you're going to have two peaks on either side of that valley representing where the valley is your intermediate and the peaks on either side are going to be your transition states. But in order to even get to this transition state, we have to make it more likely. And so we can do this in a couple of ways. And so we're going to look at how acid and base catalysis can either strengthen the nucleophile or strengthen the electrophile, and how other things like metals can help stabilize the charge on the transition state. And all these enzymes can kind of all provide interactions with this transition state that are going to help lower the energy required to actually get there. And then once it gets there, which way it goes is going to depend on the overall thermodynamic favorability of the reaction, which is something that that enzyme can't change. But by doing it in little steps where each step isn't quite as bad, it can do things like make it easier for the reaction to happen. And later in the course, we'll look at how by kind of controlling the concentrations of the products and the reactants, we can favor one direction or the other.
So you're always going to have a transition state on either side of your intermediate. Because remember, to get from one form to another, to get from that point when you're stuck on the scissors, say, to that point when you've released things, you're going to have to actually change. You're going to have to release things. You're going to have to break something. You're going to have to do something. And so you're going to have a transition state to get to the next point. This could be to get back to the substrate. This could be to go forward to the product, but there's always going to be this hump. So you're going to have a transition state on either side of your intermediate. And if you have multiple intermediates, each of these is going to have a transition state. And things can get really, really complicated where you have a lot of transition states and a lot of intermediates. But the only one that's going to matter the most is going to be the one with the highest activation barrier. And so sometimes they can have ones that are pretty similar in their activation barriers, but often you're going to have one that's really the rate limiting step. And it won't always be the first one, as we saw in a couple other examples, but one of them is typically going to be have the biggest delta G double dagger. Try to answer these following questions. How many intermediates and transition states does each have? Rank them from least to most thermodynamically favorable, and tell me which happens easiest and thus fastest. Okay, let's start with how many intermediates and transition states. They made it kind of easy in these figures because it's like int and TS3 or TS, so intermediate and transition state, but you would be able to know based on looking for the troughs. And so each of these is an intermediate, and then each of these is the transition state. And so this one would have 2 intermediates, 3 transition states. This would have 1 intermediate, 2 transition states, and this would have 3 intermediates and 4 transition states. And remember, the intermediates are going to be the kind of like isolatable things, and these would be the transition states. That's our tipping point. That's the thing that we really care about, but we can't actually capture it. Okay, which is the least to most thermodynamically favorable? So remember, what do we need to think about when it comes to thermodynamic favorability? Yeah, we need to think about our overall delta G, the difference between our substrates and our products. And so we need to be looking at the start and at the end. We can ignore everything else that happens in between. So it's kind of hard to tell with these diagrams, but let's say we draw a line over to here, and over to here. And now we want to see, like, what would our delta G be? Well, here they're pretty similar, so that wouldn't be that favorable. So this would be R1. How about this one? This one's more favorable than the first one, but is it more favorable than this one? No. So this would be R2, and this would be R3. So the first would be our least thermodynamically favorable, but still favorable slightly because it's got a negative delta G. The second is going to be more favorable, and then the third is going to be the most favorable. So remember, that's telling us about if you let them reach equilibrium, we'd expect that we'd have more of our products, the most products in the case of number 3. But which is going to happen easiest and thus fastest? Now what do we need to consider? Now we need to consider our delta G double dagger. And so if we consider that, well, we've got a big one here. We're up to about 100 kilojoules per mole. For this one, we're a little under 75. This one looks like we're about a little over 75 as well. And so basically what's going to happen easiest is it's going to be 2 and 3, and the hardest is going to be 1 because it's got the highest activation barrier. So be forewarned that coordinate diagrams can get really, really complicated, and don't worry about those. All I need you to do is be able to look at a coordinate diagram, recognize what is like where the intermediates are, where the transition states are, use them to identify if overall the reaction is thermodynamically favorable, and identify what the rate limiting step would be. So if we look at what would be the rate limiting step here, well, it looks like although TS3 is going to have the highest free energy, it actually looks like it's going to have a smaller activation barrier than getting from this INT3 to this TS4, to this transition state. I want you to be able to kind of follow the flow in these diagrams and be able to kind of identify the changes that are going on and some of the strategies that enzymes are using to help make those changes possible. So remember that enzymes are biological catalysts. They speed up reactions without being used up in the process. And the way that they speed up these reactions is basically by lowering the activation barrier. They can do these in a variety of ways, including making lots of weak interactions with the substrate that are going to help provide the binding energy to offset the cost, and they're going to provide specificity. Sometimes the enzymes actually get directly involved in the reaction by like forming covalent intermediates. But often it's just going to be non-covalent interactions. And even if it has covalent interactions, it's also going to, the bulk of the power is really coming from that non-covalent stuff. Sometimes enzymes work with helpers. They have metal ions, or they have other organic groups. Remember that substrate is just the name for the thing that the enzyme binds and acts on. The substrate binds to the active site and gets changed into products. The enzyme catalyzes things in both directions, forward and backwards. It can't change the equilibrium. It can only make the reaction get there faster. Sometimes it does these through complicated pathways, but when you're looking at a reaction coordinate diagram, note that the intermediates are going to be the valleys in between the peaks, and then the peaks themselves are going to be the transition state. Remember, transition states we represent with that double dagger. That's kind of the tipping point, and it's so unstable that we can't even see it. We can't even isolate it. And it's that point that the enzyme is going to hug the most, care the most about. And so that's where you're going to have the most of those favorable interactions. And so enzymes are often the active site's kind of going to look like the transition state, that really uncomfy state. But in order to get there, you have to have a sort of induced fit where the enzyme's kind of changing shape gently around the substrate, providing that binding energy, getting it to that transition state, and helping make that easier to get to.
Next lesson, we'll go back to our main catalytic strategies I briefly mentioned. We'll talk more about acid-base catalysis, as well as proximity catalysis, so holding things together, metal catalysis, when those metals get involved, covalent catalysis, when we're actually forming bonds between the enzyme and the substrate that then get broken later. We'll also look at specific examples and talk about how we can classify enzymes based on the kind of strategies they use and the reactions that they catalyze.